In this lecture, we discuss one very important aspect of HDF5, the ability to do partial I/O, in other words, to read or write only sections of a dataset that we want. In many real-world problems, the amount of data is small enough that we can load the entire thing into memory and do whatever operations we want there. For example, if we have a CSV file, we might write a Python script that reads it into memory and performs operations. Generally speaking, the quantities of data are small enough, there's plenty of memory left over. And if we wanted part of the dataset instead of the entire thing, we can simply chop that piece out after it's loaded. This approach works very well for small files and small datasets. However, as the files and datasets become larger, we begin to run into problems. For example, the amount of time it takes to load data from disk can become very long. Also, for very large datasets, we may come close to the limits of available RAM in the machine. And even if we don't exhaust the memory, the use of paging means the computer performance may slow down. Particularly in cases where we want to do a subset of the data, loading the entire set of data into memory and then performing the subset is very wasteful. HDF5 addresses this problem by supporting a technology called partial I/O. In partial I/O, we specify the region of data we want and then read only that piece of data from disk. This avoids the problem where we load the entire set of data into memory and then perform reduction. Common applications include faster I/O when you only want to work with a section of the data, and for files which are simply too large to fit in RAM, this becomes the only feasible way to interact with data. If you want to update only one section of the data, we can also read, modify, and then write back only that portion of data we care about. HDF5 supports a number of techniques for specifying the region of data to access. For example, you can retrieve a contiguous piece of an array, all in one block, or a regular pattern, arbitrary selections of elements scattered throughout the file, and of course, combinations of the above. Let's consider an example and see how partial I/O can work. First, we're going to create an example dataset using Numpy, which is simply a 10 by 10 array holding the first 100 integers from 0 to 99. Let's double check the shape and dtype of this array. We see that the array is 10 by 10 and has a data type of int64. Then let's create a new HDF5 file and create a dataset inside the file that holds this data. We use the data keyword to initialize that dataset with our array. Now we have the dataset object, dset. As we saw before, HDF5 dataset objects have very familiar attributes, including shape and dtype. But if we investigate closer, we can see that the dataset object is, of course, not a NumPy array. However, we can treat this object much like a NumPy array. For example, if we wanted a particular element, say index 4 and 5 of our two-element array, we can simply use the Numpy indexing syntax to retrieve that element. And if we look at the type of the return data, we can see that applying this indexing syntax actually will retrieve real NumPy data. So what's going on? Well, when we apply a NumPy indexing to our dataset object, HDF5 is figuring out where that element lives on disk, then loading into memory, then performing any type conversion required to adapt that data into one of the NumPy types, and finally returning it to NumPy. In computer terms, this is an example of something called lazy loading. In other words, when you create a dataset object in HDF5, no data is actually loaded from disk. Only when you apply the NumPy indexing syntax does HDF5 actually go to disk, find the elements that it wants, and retrieve them. And although the dataset reports its shape as 1010, all that information remains on disk until it's required. Now that we've seen how to use NumPy indexing to access pieces of the data, let's think about how to access multiple values. One simple way for our two-dimensional dataset is simply to use a pair of nested for loops, one of which iterates over the x index, and the other one which iterates over the y index. In this example, we try to iterate over every index in the x direction and every other index in the y direction. Take a minute to think about the performance of this code. Unfortunately, it does not perform very well. Because this code reads element by element, HDF5 has to translate that request into a portion of the disk, find it on disk, read it, perform type conversion, and then return the data again and again and again. So we need a more efficient way to load multiple elements at once. It turns out there's an established technique in Numpy to do this. It's called slicing. For example, let's suppose we wanted to retrieve one section of a particular row of our data set. We'd use the syntax in square brackets 2, followed by a slice from 0 to 5. What this does is locate row index 2, then specify we wanted elements 0 to 5 and the other dimension, pick those out, read them into memory, convert them to a NumPy compatible type, and then return them. Importantly, the object we get back at the end of this process is a real NumPy array. Crucially, HDF5 only needs to perform the steps of locating the data in the file and performing the type conversion once for this entire set of data, instead of again and again and again in the case of indexing one element at a time. Of course, we're not limited to reading just contiguous blocks of data all at once. Suppose we wanted to read every other element along a particular dimension. In this example, we want to read the first row, row 0, and every other element along the column direction. So HDF5 goes out and finds the first row, then it locates every other column, reads that information, combines it into one array that can be returned to memory and to NumPy. And of course, if we wanted to read the entire data set, assuming it would fit, we can then retrieve the entire contents of the HDF5 dataset as a real NumPy array. Let's take a moment and think about how slicing would compare to our previous index example. Here's that code again with a nested for loop that reads every other element along the y direction. And, by comparison, here's the faster slice-based version that does the same thing. Keep in mind the difference is that HDF5 has to perform these steps requiring overhead only once in the case of a slice-based version, and for every index in the case of the indexing version. Let's take a look at a real-world example of how the HDF5 technologies of partial I/O and slicing can help you interact efficiently with a large HDF5 file. Let's imagine that we'd received from somebody else a large HDF5 file called big.hdf5 that, if we investigate further, has a size of almost 4 gigabytes. Clearly, we want to avoid loading all this information into Python all at once. So we'll use the h5py package and HDF5 partial I/O to read and update only the parts that we want. Start by launching Python, then import h5py. We can open the file. Once we have the file open, we can investigate the contents of the root group by using the dictionary-like methods. And we see the file contains just one object, a dataset called big. We retrieve the object. Now we can investigate the HDF5 dataset. Let's examine the shape first. This gives us a hint as to why the file is so big. The dataset shape is 1000 by 1000 by 1000. In other words, a billion elements. If we then examine the dtype property, we can see this dataset stores 32-bit integer numbers. At 4 bytes per number, that means this is almost 4 gigabytes in size. Thankfully, we don't need to load the entire dataset into memory. We can access individual elements. For example, if we wanted the first element, we can use 0 for all 3 indices. Or, if we wanted to access an arbitrary element somewhere in the dataset, we can retrieve that value. And of course, we can update that value to whatever we want. And that value is reflected immediately in the HDF5 file. If we want to load a range, for example, we wanted to load every other point along the last axis of this particular section of the dataset, we can use the slicing syntax. and HDF5 returns just the piece that we want. For example, if we wanted to load the first 10 elements, we get just that portion of data. Suppose we wanted to read all the information from this file into Python, but not all at once. We can use HDF5 partial I/O in combination with slicing to do this. For example, since the shape is 1000 by 1000 by 1000, we can write a loop that iterates over the first index and reads only 1 million elements at a time. In this way, we can operate on one piece of the data at a time and avoid becoming overwhelmed. When finished, we close the file. To summarize, partial I/O is an extremely valuable technique for reading from disk just those pieces of data that you want. It completely avoids the issue where a dataset is too large to fit into memory before reduction is done. HDF5 supports a very sophisticated system for specifying which portions of data to retrieve. And if you use the h5py package, you can use the very familiar NumPy slicing syntax to access data in a familiar Pythonic way.